Hello, my friends. Welcome back. In the previous videos, we talked about how we can optimize a design so that it can give us a higher throughput. That was the first example. And then the second one, we saw that we can take the same design, basically remove all the pipeline stages and make it an optimized design with respect to the latency. And as I promised in today's video, I want to talk about timing optimization. Timing optimization is a bit more complicated than the other two, so I cannot just give you an example. Be okay, like this is how we can take the Power 3 example that we had and make it optimized for timing. So I need to talk a bit about what timing is and the different methods that we could use to optimize the design for timing. So as we talked about it before, timing refers to the clock speed of a design. So the maximum delay between any two sequential elements in a design will determine the max clock speed, right? So there are, as I said, different methods and trade-offs that we need to consider when it comes to improving time and performance. The first technique to optimize the timing is to add register layers. So this is the first strategy for architectural timing improvement. What is that? To add basically register layers. How does this work is that this technique should be used in highly pipeline designs where an additional clock cycle latency does not violate the design specification and the overall functionality will not be affected by the further addition of registers. An example of this, if you may ask, I could just give you an example here. So let's say that you have a design, right? And it's like when there is clock, or like if you rather like the rising edge of the clock or however you want to word it, do like A equals like function A plus function B or 1 or 2 and so on and so forth. So in this example, in this one clock cycle, you're doing all these. You're calculating function 1, you're calculating function 2, and I did use the add sign here, but it means just like combining the output of those functions in any way that you want, right? It could be like an adder followed by a multiplier, which is like called a MAC unit, multiply add, right? And it's like a very basic unit in neural network and AI applications, for example. So in this example, you're just like having a very large path, right? And this is not going to give you a good timing. So what you can do is to break it down into different clocks. So you say, for example, when clock, right? You can go, for example, I don't know, X is function 1, Y is function 2, and so on and so forth. And then, like you can go A is X plus Y. And this addition sign, just like this one in here, is just like how you want to combine them. In this example, what happens is that in the first clock, or in each clock, you're calculating function 1, you're calculating function 2, and that's it. So instead of like calculating all these and combining them, you're breaking it down by adding register layers to just like one function at a time, and then you just combine it. So it's like it takes more clock cycles, obviously, but it's like shorter clocks and it's improving your timing. So that's the first technique that you can use. The second one is to use parallel structures. This is the second strategy for architectural timing improvement, right? And it is basically to reorganize the critical paths such that logic structures are implemented in parallel. This technique is usually, and like it's better to be used whenever the function they currently evaluates through a serial string of logic can be broken up and evaluated in parallel. Okay, I know it can be confusing. And before we go any further, I want to tell you that in the next video, I want to give you examples of these. I want to talk about add register layers and then like show you two example, like an example of the regular design and then how we can add register layers. I also want to show you an example of like another design and like how we can improve the timing by, parallelizing the structures, right? In this video, I just want to talk about the different techniques so your mind is ready for what's coming next. So an example of parallel structures is that, let's say you want to do some multiplication. So you have like an 8-bit maybe multiply, right? So you have like an 8-bit multiplier, right? And then you want to divide it, you want to break up the operation into two or like four 4-bit multiplications, right? So you can go like my 8-bit number is A plus B, right? This is the first one, and this is multiplied by C plus D, right? And in C and D and A and B obviously are not just like added as we see the symbol here. It's just like a sign that they're combined. So basically A is a 4-bit number shifted 8 times, right? 4 bits. And then or with B, same goes with C. It's a 4-bit value which be shifted 4 times and then added with D. So you do these calculations that now you're performing 4-bit multiplications instead of 8-bit multiplications, which is much, much, much shorter so that it can improve the timing. Hopefully that's clear. But if not, don't worry about it. We'll see examples in the next video. The third technique would be to flatten logic structures. What does this mean? It means that, flattening the logic structure is closely related to the idea of parallel structures, but it usually applies specifically to logic that is chained due to priority encoding, right? So typically, synthesis and layout tools are smart enough to duplicate the logic to reduce fan out, right? But the problem is that they're not usually smart enough to break up the logic structures that are coded in a serial fashion, nor do they have enough information relating to the priority requirements of a design. So it all comes down to, it's obviously gets easier if I give you an example. So here it is. If I go, if condition A, like I just go cont 1, then do this, and then else if condition 2, then do this, and then else if condition 3, then do this, and then else do this. So this is a very complicated design. It usually gives you a back timing. I can have the same functionality by saying if condition 1, then do this. If condition 2, then do this. Obviously, whenever it's possible, right? If the conditions are not mutually exclusive, or like they have weird priorities and stuff like that, then you need to be more careful. I'm just giving you a general idea. So if you can code like this, the one on the right, and you do it like this, well, this is not a good practice. The fourth one is register balancing, right? So conceptually, the idea is to redistribute logic evenly between registers to minimize the worst case delay between any two registers. So basically, you don't want to have one super long path and like short paths as well. If you can balance them out somehow, you should do that. This technique should be used whenever, the logic is highly imbalanced between the critical path and an adjacent path. Like as I said, like when you have a long path, which is your critical path, and then like there's like a bunch of short paths nearby. It's not always possible. So again, keep in mind that these techniques are like you need to use them based on the problem that you're facing, right? And an example of this, I mean, it's pretty clear. You don't really need an example, but basically, you don't want to do that. So adding register layers and like this registering balancing could be seen like somehow similar. I would say that, okay, for example, adding the functions, and then let's say here you have, I don't know, b equals func 3, and then c is a plus b. So you'll see that like this is super long, right? And this is short, and this is your critical path, for example. So register balancing would basically say that, okay, if you can break it up into different, paths, so you don't have one super long path, so that like it messes up and screws up your timing, and just like have a few longer passes, right? Still shorter than the main path, the critical path that you had before, but it's a more balanced design. Anyway, and then the fifth one, which is the last technique that I can think of, there could be more honestly, is to reorder the path in the data flow to minimize the critical path. So this technique should be used when multiple paths combine with critical paths, and the combined path can be reordered such that the critical path can be moved closer to the destination register, right? So with this strategy, we will only be concerned with the logic path within any given set of registers. Hopefully that makes sense. These are the 5 main time optimization techniques. As I said, this is just an introduction. In the next videos, we will be seeing examples of it. Like I'll have examples from adding register layers, parallel structures, flattening logic structures with register balancing and reordering paths, and we'll compare them on parallel. Be like, okay, this is how like one design, and then this is how we can add registers to make it like more optimized with respect to timing. So hopefully next video will help you clear things out a bit more. But this gives you a good idea, and you can think of something yourself based on the explanation that I give here. And you can think of something. And if you had any question, please do not hesitate to ask me in the comment section. I'd be more than happy to answer those. If you haven't already subscribed to the channel, please do. And if you like this content, please like the videos. It's gonna help me a great deal. And as always, thank you for watching me. See you guys all in the next video. Take care. Have a good one. Bye bye.